Hello viewers, welcome back to another section of my tutorial. In this video I have a differential equation tutorial, and the problem I have here is a second order linear non-homogeneous second order differential equation. Take note of the classification. It is second order linear non-homogeneous differential equation. So let's see, whenever you are to solve non-homogeneous second order linear differential equation, we have two ways: either use the variation of parameters or method of undetermined coefficients. So in this tutorial I'm going to use the variation of parameters. Let me make it VOP, variation of parameters. So how do you go about that? Now, always whenever they give you a non-homogeneous second order differential equation to solve, write down the general, or write down the complementary solution. So you are going to get, writing the homogeneous form, you are going to get y prime prime minus y is equal to 0. So this is the homogeneous form of this non-homogeneous. So meaning this term here is making the whole function non-homogeneous. So in this form it becomes homogeneous. So how do I get the complementary solution from here? So we know that you write a characteristic equation. And how do you get a characteristic equation? This is given by the coefficient of this. So I'm going to get r squared minus 1 is equal to what? 0. From here I'm going to get r squared to be equal to 1. Therefore my r will be equal to plus or minus 1. So I've got the two values for r, and since it is distinct real roots, I'm going to have my yc to be simply equal to c1 e to the power, taking the positive 1, x, let me make it x, then plus c2 e to the power negative x. So this becomes my complementary solution. We are almost halfway through. Now, in method of variation of parameters, always the particular solution is dependent on the complementary solution. So we are going to write our yp to be equal to, instead of c1, that's going to be u1 e to the power x, then plus u2 e to the power negative x. So this becomes our particular solution. What are we left to? We are left to find our u1 and what u2. Then we get our complete particular solution. So let me divide my workspace so that I got a space too. So once I have this, to find u1 and u2, how do we go about it? This is where we apply the Wronskian W. So to find the Wronskian of this function, it will be equal to the determinant of e to the power x, then down here will be the derivative of this. So I'm also going to get e to the power x, then also here is going to be e to the power negative x. When I differentiate this, I'll get negative e to the power negative x, like this. So finding the Wronskian is simply equal to the same as finding the determinant. You cross here minus you cross here. So when I multiply this, I'll get e to the power x multiplied by e to the power negative x, then minus the expression e to the power x multiplying e to the power negative x for the Wronskian. So my Wronskian here is going to be negative, I'll add x plus negative x, that will give me 0. So negative e to the power 0, then minus e to the power another 0 here. So what do I get here? Minus 1, then minus 1, giving me negative 2 as my Wronskian. So once I get this, I'll put this one down. Then I apply the Kramer's rule to solve for u1 and u2. So we have this system of equations I'm going to write here. So I'll write this thing, the same thing here. That is e to the power x, e to the power x. Here will become e to the power negative x, e to the negative e to the power negative x. Then this multiplied by this multiplied by u prime 1, then u prime 2. The reason is, before we will get this, we will first differentiate this yp and put it back into the original equation, but it's going to give us a system of equation which can be solved using the Cramer's rule. Then after our solution here, always we write here to be 0, and the last one is going to be that of the g of t from our non-homogeneous equation, and here is e to the power x. So I'm going to get e to the power x here nicely. How do I get my u prime 1 then u prime 2? Applying the Cramer's rule, I'm going to take, for u prime 1, I'm going to remove all this and put the 0 e to the power what x, then here will be e to the power negative x minus e to the power negative x, like this, multiply by, as it is. Okay, so for the Cramer's rule, as we have this here, we are going to find the determinant of what you have got here. Determinant. So let me rewrite it all so that you see it all. So if I write it this way, I'll get 0 e to the power x, e to the power negative x, then negative e to the power negative x, to a negative e to the power negative x. And what is this going to give me? So when I get this, by Cramer's rule, I'll divide this whole expression by my w, negative 2, and that will be equal to u prime 1. So let me solve what I have here. So when I cross multiply here, I'm going to get 0. So I'm going to get 0 minus the expression e to the power x multiplying e to the power negative x all over negative 2. Now here they will add, and I'll get to the power 0 to be 1. So it will be equal to negative 1 over negative 2, which is the same as 1 on 2, and that is u prime of 1. So once I've got this, if you have u prime of 1 to be equal to half, then my u will be equal to the integral of 1 out of 2 dx, which is the same as x over 2. So I'll put my u1 down. So I've got my u1. Now I come back to the Cramer's rule once again to find my u prime of 2. So to find my u prime 2, it is equal to the determinant, then I'll bring this thing back again, this e to the power x, e to the power x, but for this side I'm going to replace it with this part on the y side. So 0 here, I'm going to have 0 here, then e to the power x, so I'll get e to the power x here, then all over the negative 2 for the u prime 2. So here too, I know that when I cross multiply this, I'm going to get e x multiplying e x minus 0 over negative 2, and this is simply equal to, here when you are multiplying, the powers will add, e to the power 2x over negative 2. So that is my u prime of 2. So if I have u prime of 2, I can find my u2 to be equal to integral of negative e to the power 2x over 2, integral of negative e to the power 2x over 2, and dx, and that's going to give me negative 1 out of 2 integral of e to the power 2x, and by substitution I'm going to get my final solution to be negative 1 over 2 times 1 over 2 multiplying e to the power 2x, and that's giving me negative 1 on 4 e to the power 2x. So I have my u1, I have my u2, I'm almost done. What do? I substitute it back to my yp, my particular solution, which was initially u1 e to the power s And now my u1 I found it to be x over 2. So I'm going to have x over 2 multiplying e to the power x. Then I have plus u2, where my u2 now is negative 1 on 4 e to the power 2x multiplying e to the power negative x here. So multiplying e to the power negative x here. But once I have this, I'm going to get x e to the power x all over 2 minus 1 over 4. When I add, I'm going to get e to the power x like this, because I'll get 2x minus x, the same base, the powers will add. So that is how we go by it. So now this is what I'm getting for my yp. So once you get yp, you know that you are almost done with your solution. Just that the general solution is always equal to yc plus what? Yp. Therefore, from my yc, and yc was c1 e to the power x, so c1 e to the power x, then plus c2 e to the power negative x, then plus my expression x on 2 e to the power x minus 1 over 4 e to the power x. So this is a general solution from the method of variation of parameters. Thanks for watching. Kindly subscribe to support, and don't forget to like as well.